Hello and welcome to our first discussion in Chapter 3, Periodic Properties of the Elements. Things that we want to start off with in this section is just looking at elemental patterns and why we have the periodic table. So reoccurring patterns that we see for both physical and chemical properties really aid us as chemists at predicting new elemental behavior and studying new types of reactions for elements. So for instance, aluminum versus indium, aluminum's density is low. It's 2.7 grams per centimeter cubed. And when compared to indium's density, 7.31 grams per centimeter cubed, um, we can start to see that as elements, as we move down a column on the periodic table, aluminum is in row 13 on the periodic table, or column 13, excuse me, and indium is just two specific rows down. And what we see is that the density of elements tend to increase as you move down a column. And that's primarily due to the mass to volume ratio of the atoms increasing. And density, along with other patterns such as atomic radii and affinity of electrons, probability of losing an electron, all of those things tend to be familiar. And so when we start looking at the periodic table, we'll start looking at how can we look at an element's position on the periodic table and say something about it? Is there somebody next door that is similar in reactivity? And that's where we'll be able to really use the periodic table as a tool. You will always have a periodic table with you when you take an exam. That is not something that I need you to memorize, but what we want to be able to do is look at that periodic table and truly use it as a tool. Let's just get into a couple of elemental patterns. First, density was one. Atomic radius is another one. When we look at moving down a column, so this is just a pulled out version of that same column where we had aluminum and indium in the previous example. And what we see is density does increase. Boron's density is the smallest. Indium's density is the biggest. And what we see also is the radius increases with 85 picometers for boron all the way up to 166 picometers for indium. We'll talk about more about these trends and what really causes these trends. It's going to relate back to chapter 2 and our quantum mechanics. But what we want to do first is really get a good review on who developed the periodic table. In 2019, we celebrated the 150th anniversary of the periodic table. Dmitry Mendeleev in 1869, he was a Russian chemistry professor, and he arranged the elements that were known based off of mass. It's actually a really funny story. Dmitry Mendeleev, very secluded chemist, he loved to play solitaire. And I imagine him just kind of sitting in his house with maybe a lab coat on because he's cool like that, playing solitaire and putting one element on each card. And what he noticed was as he would line up these elements, notice how you see here, when he would line up these elements by mass, he actually noticed that there were some reoccurring properties. Things like helium and neon and argon were what they call inert gases, things that do not like to react with other elements. Same idea with lithium, sodium, and potassium. These were elements that were metals, and they had a very violent reaction with water. So they all had to be kept under oil. When they were stored, they could react with the moisture of the air, and when they did react with moisture, they were explosive. Again, he went a little bit further and said, well, beryllium and magnesium and calcium all kind of react the same. They're not as violent as lithium and sodium and potassium, but they still do react slightly with moisture in the air and specifically with water. And so looking at how Mendeleev set up the periodic table, he was doing it first off of the idea of increasing mass. And then what he noticed was that certain elements had very similar properties. And so he started to line up those elements. Think about solitaire, how we ever played solitaire. If you learned it as a kid, it might be a lost art now, but my family was big on card games. So solitaire is one where we put the cards on top of each other, and we make columns with the cards based off of certain properties, red versus black, an order of numeric value. So what Mendeleev was really doing was starting to look at a couple of different properties, physical and chemical, so mass and reactivity, and align these elements in a specific way that made sense to him. What's amazing about this is that quantum mechanics, which was discovered or developed, 70 years later, actually explains the electronic structure of the atom and its properties. And therefore, when we look at the periodic table, we can see the beauty of how it was set up, not only by simplistic things like mass and reactivity, but also see how quantum mechanics plays a huge role in its organization. The modern periodic table, what's its format? The elements, again, are still listed in order of increasing atomic number. Why we don't do increasing relative mass anymore, as they were on Mendeleev's table, is that we know about isotopes now. And so there are some very rare cases where an element with a larger proton count actually has a lower mass. And that's only due to the fact that isotopes exist, and some isotopes are more abundant than others. So we do it by something that's a little bit more concrete now, which is atomic number. It is increasing in atomic number, so we do have that structure on our periodic table. The rows going across a row is often called a period. Going down a group is often called a family. Sometimes they're called groups, going down that column. But like I said, they have that familiar type of physical and chemical properties. So things like helium, neon, argon, they're part of the same group or family. They are called the noble gases. We do have fluorine, chlorine, bromine is underneath that, and iodine, those are called the halogens. The only one that is kind of left out is hydrogen. Hydrogen is over there in column number 1. Column number 1 are called the alkali earth metals. We'll get to those specific names a little bit later. Hydrogen is not really part of group 1. It's over there because it's the first element, but in reality, where it should fit is very similar to fluorine, chlorine, bromine, and iodine. It's not the same, it's kind of in between. So hydrogen is in its group all by itself. It doesn't even have a family. Kind of sad, but he's actually multiple families. Mendeleev, again, developed the periodic law and the periodic table. He put the elements in patterns, but he did not explain why the patterns were what they were. He was really amazing at predicting which spots needed a filler element, or how many families they had that there were at that specific time. However, he knew nothing about how the actual elements reacted. And so the periodic table is specifically a law. It predicts the patterns, but it does not explain why. It is not the theory behind anything. Quantum mechanics is still our theoretical basis for how and why things react. Okay, groupings. Again, we'll see a couple of different ways to talk about the periodic table. What I would suggest at this point is pulling out a periodic table again, and kind of honing in on these specific groups as we dive into it. I know the online format's not the best. However, we'll do a lot of this practice in class. The periodic table can also be divided into main group elements, and those are elements whose properties are very, very predictable. The main group elements, if we just count across, it's the middle section from scandium to zinc. Those and their families are what we call the transition elements, and the inner transition elements or transition metals are the lanthanide and actinide series. Now, the transition elements, the lanthanides and actinides, they have somewhat predictable properties, but not a whole heck of a lot. When we look at them, yes, we can kind of see some trends, but there's really variations with them. And that's pretty much because of where their outermost electrons are. So we're going to get into looking at this periodic table and being able to really start to label things. Again, here's some things that we talked about: main group elements. Your textbook has both the A's and the B's, and also 1 through 18. Old school is the A's and the B usage. There's the B's for the transition metals. You can also see a new method where we just go straight across and count 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 18. Doesn't change anything, it's just a way of counting, right? So the main groups are the A's, or 1, 2, 13 through 18. And the transition elements are the B's, or 3 through 12. Either way you slice it. Again, the inner transition elements, right there, the lanthanides and actinides, they are just as unpredictable as the transition elements are. You can call them transition elements, or you can call them transition metals. They are metals. Now, when we look at the metalloids, some periodic tables like this one here, which was from the e-text version of your textbook, doesn't have the metalloids on there. So I'm just going to highlight them as purple. We have boron, silicon, germanium, arsenic, antimony, tellurium, astatine. That guy, the new one, 117, brand new. I don't really know what his name is yet. So what we see is the step down ladder that really separates our metals and our nonmetals. And that ladder you can kind of memorize as looking at where that transition is from metal to nonmetal. We're going to talk more about what does that mean and their reactivity when we get into periodic trends. Again, you do not need to memorize those things, but you do need to be able to look at a periodic table and identify where the metals, where the nonmetals, where the metalloids, where a transition versus main group elements. So again, things on the left are metals. This little corner over here on the right are the nonmetals. Lovely. All right. Now, we just came from the quantum mechanics chapter, and it was able to describe quantum numbers. When we took our quantum numbers, we were able to really locate the probability of finding an electron in the electron cloud. And so quantum mechanics is describing the behavior of electrons in atoms. We know where they can be found based off of the probabilities of quantum numbers. Now we're going to take those quantum numbers and change it into what we call the electron configuration, how an atom's electrons actually occupy the orbitals. We've discussed all the different orbitals and all the different options with quantum numbers, but now let's put it together and put it with the elements themselves. So when we left chapter 2, what we ended up saying is n can be any whole number 1 through infinity, but L is determined based off of n. N is the size of the orbital, it's the distance away from the nucleus. It also tells us the energy of the orbital. L tells us the shape. When L equals 0, that's the s orbital. From there, we can think about the ML and say that that is the range from minus L to plus L, including 0. And we do know that there is a spin of either plus 1/2 or minus 1/2. Now, what we can do with that is do a shorthand. We'll take the N value, we'll take the shape of the S value, and we'll be able to merge those together into an actual orbital location. Now, that orbital, 1 being N, and S telling us L, that tells us a lot of information about the energy, the size, and the shape. The number up here at the top in the subscript is telling us information about the electrons that we can put in there. And that's the new part in chapter 3 that we're going to be able to discuss. Now, hydrogen has only 1 electron in its elemental form. And so with that 1 electron, we want the simplest orbital that we can find. And that's what we'll see. When an electron occupies an orbital for an atom, it's going to try to be the lowest energy possible, the simplest energy possible. We know that the lowest energy would be n equals 1. And when n equals 1, that gives us an s orbital. And hydrogen can put its 1 electron in there. So we have an electron configuration for hydrogen of 1s1. That's how we would read that. You can also say 1s superscript 1, but I just like to say 1s1. That's the identity. Let's talk a little bit about the Pauli exclusion principle. This is where we actually get into the idea about m sub s, the spin, being plus or minus 1/2. What does that even mean? Well, when we think about an orbital with a specific orientation, there can be 2 electrons in that orbital. That's what quantum mechanics is developing. The idea that we could have hydrogen, I'm going to rewrite hydrogen with its 1s1 electron and its orbital diagram, which is usually just a box that has the orbital name, the N and the L. It has 1 electron in there. But when we look at helium, why is helium so stable? It has 2 electrons, 1 meaning that N equals 1, S meaning that L equals 0, and that 2 up there tells us there are 2 electrons in that orientation. Now, we do know that ML equals 0, and how we get the 2 electrons in that orientation is by having one have an ms of plus 1/2, and the other will have an ms of minus 1/2. The Pauli exclusion principle says this: no 2 electrons in an atom can have the same set of 4 quantum numbers. Their N, their L, and their ML can all be identical, but what has to be different is the spin. And so when we think about that, we can have a maximum of 2 electrons per orientation. As we go and increase N, we know that L can have more options, and so then ML has more options. The only options we ever have for the MS is a plus 1/2 and a minus 1/2. They must balance each other, those electrons. And so no more than 2 electrons can exist in a given orbital. Okay, a couple of things. That idea of the Pauli exclusion principle was not developed until 1925, still in the time of quantum mechanics. It was discovered or developed by Wolfgang Pauli, who really was trying to emphasize the idea of energy levels of electrons. A couple of other things that came out of this. The Pauli exclusion principle, I want to just rewrite so that we can know it's one of our home plates, right? It's one of our ideas that we have to carry throughout our discussion on electron configurations. Another one is called Hund's rule. Now, Hund's rule is the idea that degenerate orbitals have the same energy. We'll call that equal energy. So what are degenerate orbitals? They're orbitals of the same shape and size, just different orientation. So when we look at something like n equals 2 and L equals 1, this was the 2p orbital. ML, though, is -1, 0, and +1. There were 3 orientations, and if we remember, they were the X, the Y, and the Z. Now, in electron configuration, we again as chemists like to abbreviate things as much as possible. So when we think about the px, the py, and the pz, they will all be encompassed in that 2p, and they're understood to all be there. There are 3 orientations, and each orientation can have 2 electrons. Why can it have 2 electrons? Because of the ms of +1/2 and -1/2. Each one can have a +1/2 and a -1/2. So 3 orientations, 2 electrons in each. To fill the 2p orbital, we can have 6 electrons. Now we'll learn a little bit more about Hund's rule. I want to just present it right now, but we won't fill up our diagrams for a couple more minutes. When we look at Hund's rule, the last portion of it says that because degenerate orbitals are equal in energy, right? Because the px, the py, and the pz are equal in energy, when putting electrons in these orbitals, when we start to see that how they react in the electron cloud, one electron gets put in each orbital first. Before pairing. What we're trying to build here is a couple of rules that help us overall understand how the electron cloud is formed as we put 1 electron, 2 electrons, 3 electrons, etc., all the way up. How do we build up the electron cloud from 0 all the way up to, let's say, 8 electrons? Pauli exclusion principle is the good first one. No 2 electrons can have the same 4 quantum numbers. Hund's rule is the second really good rule to follow. When we have degenerate orbitals, the px, the py, the pz, the same thing goes for the 5 orientations of the d orbital and the 7 orientations with the f orbitals. We put 1 electron in each before we pair. Let's just draw that out, 1 in each, so that each electron could have its own space before it pairs. If we have to pair, we will, but we'll try to give every electron its own space first. Now, along with these orbitals, we do have one more idea, and it comes from our last principle, which is called the Aufbau principle. The Aufbau principle literally is German for build up. It means that in order to build up my electron cloud, electrons are placed in low energy orbitals first. and we build up the electron cloud from there. So yes, that means that n equals 1 is lower in energy than n equals 2, and etc., right? But also, the energy of the s orbital is lower than the energy of the p orbital, and it's lower than the energy of the d orbital. The highest energy shape we have is the f orbital. So even with L values, L equals 0, 1, 2, and 3, we still see that idea of changing in energy. Why? Well, it has to do with a little bit of Coulomb's law. How many electrons are we putting in there? For the s orbital, we have one option for ml, so 2 electrons total. When we have the p orbitals, we have 3 options for ml, which would be 6 electrons total. More electrons, more repulsion, higher energy. For the d, we have 5 options for ml, so that is 10 electrons total. And for f, we have 7 mLs, so 14 electrons can technically fit in that f orbital group.